efficiency. Now we are going to see what all the losses we have to consider when you are going to find the efficiency of transformer. So first one, major one is copper loss. Copper loss, or it is called as I square R loss, and PC is equal to I1 square R1 plus I2 square R2. It is because of winding in the primary and winding in the secondary. So when current flows through winding in the primary and secondary, because of resistance of the winding, you will have some copper loss. So either if you consider both the primary and secondary current, it's going to be I1 square R1 plus I2 square R2. If you are transforming everything into one side, into impedance, so if you are transforming the resistance into effective resistance in the primary, it is just I1 square into RE1. If you are going to move all the resistance into the secondary, it's going to be I2 square into RE2. So these three formulas you can use it. Whichever currents are available, you can apply and get the answer for copper loss. And copper loss, you see, it is proportional to the current. So copper loss depends on square of the current because resistance is going to be constant. So copper loss is proportional to square of the current. So the output power is given by P naught equal to VI cos phi. So it is going to be VI into power factor. Cos phi is power factor. So from that, I can find VI equal to P naught by power factor. VI is your VA of your transformer. You call volt ampere, right? So VA of your transformer, if you want to find, you can use the formula P naught by PF. And this VA will be same for both primary and secondary. So for a given load, we can find volt ampere of transformer using the above relation. So volt ampere equal to output power by power factor. Okay, okay. So the voltage is going to remain constant. So current only is going to be varying. So I can say VA is proportional to current. But in copper loss, I can say copper loss is proportional to I square. So if you can relate all the things, then you can find the copper loss for any given load from the no load using this equation. Copper loss equal to volt ampere by volt ampere full load, the whole square into copper loss at full load. See, it is very simple. Copper loss is proportional to VA square. So copper loss at full load is proportional to VA full load the whole square. So if you divide both, you get this equation. And why we are squaring it? Because copper loss is proportional to I square and I is proportional to VA. So indirectly I can write copper loss is proportional to VA square. See the numerator, PC is proportional to VA square and PCFL is proportional to VAFL the whole square. If you divide, you get this equation. Okay, so copper loss is proportional to square of VA. So that is the relation. So if you know copper loss at full load, you can find the copper loss at any given load using the formula which you are seeing in the display now. Okay, so for me, the major loss which is going to reduce the efficiency of transformer is going to be the first one, copper loss or I square loss. So we have seen that. Now it is iron loss or core loss. This one we have already seen, hysteresis and eddy current loss. So in the core, hysteresis and eddy current loss will be there. Hysteresis, it is lagging behind of the magnetic field with respect to the electric field. So magnetic field is a little bit slow. So that lagging behind will cause a power loss that is going to be called as hysteresis loss. And eddy current loss, it is because of small loops of current forming inside the core because of improper lamination of your core. And this eddy current circulate inside the core causing eddy current loss. So I can write Pi equal to PH plus EPE. Pi is the iron loss, PH is the hysteresis loss, and PE is the eddy current loss. You can assume the core loss to be constant all throughout the loads. So core loss is not going to vary. So core loss is going to be constant at all loads with not more than 2% variation. So there is going to be almost, we can assume them to be constant. So when the transformer is loaded, copper losses dominate. When the transformer is unloaded, iron losses dominate. Very, very important statement. So which loss is going to dominate where? When you're not going to have any load, the iron loss is going to dominate. Iron loss means hysteresis and eddy current loss is going to dominate. When the transformer is going to have an n number of loads, then you will have secondary current. So there copper losses are going to dominate. I hope this is clear to you. Load in the sense, assume that you are connecting any appliance to your transformer. That is the simple example how you can correlate load in a transformer. So I can write efficiency as P naught by P naught plus PL, P naught by P naught plus PC plus PI. PC is the copper loss, PI is the iron loss. And P naught, see here what is P naught? We from this expression VI cos phi. So I am measuring output at secondary, so it is V2 I2 cos phi 2. Okay, secondary notation divided by same P naught V2 I2 cos phi 2. plus PC copper loss I2 square RE2. See, I am writing everything with respect to secondary, so I am writing only in terms of I2 everywhere. Plus PI I am writing it as PI because iron loss is constant. We have seen that iron loss I am going to consider it as constant for all the loads. So this is the simply final expression for efficiency of a transformer. The efficiency of a transformer is going to be eta equal to, I'll repeat, please listen, P naught by P naught plus PL. And this loss, you know, it is made up of hysteresis and copper loss, copper loss and iron loss. Iron loss is constant, so I'm not going to touch the iron loss. Copper loss, it is going to be equal to I2 square into RE2. And everywhere you see, I'm using I2 because I'm measuring everything at the secondary of your device. Primary la measure பண்ண முடியாதா? P naught is always measured at the secondary. And PC, we have three formulas, I1 square R1 plus I2 square R2 equal to I1 square RE1 equal to I2 square RE2. So the most apt formula for PC will be using I2 square RE2 because I have secondary current involved here. And secondary current is coming everywhere in the sequence. So it is advisable to use I2 square RE2 here. Okay. So this is the efficiency of the expression for efficiency of the transformer. What other losses we have? See, we didn't include some of the losses in the transformer efficiency. We are going to see what is the additional losses which may occur in a transformer which we have